This presentation is dedicated to the memory of my friend and colleague Pim Rietbroek. Pim was a great champion of Unicode in his work at the Dutch publishing company Brill, and responsible for standardizing and coordinating their text workflows and typography across many languages and scripts. I had the pleasure of co-presenting with him at a previous Unicode event and know that he will be missed by people in this community. It was a privilege to know him and to have been able to work with him over the past 2 decades. This is a Unicode technology workshop, so I'm going to begin by introducing a Unicode technology. I will talk about how that technology works and some of the ways in which it can fail to work. I will then introduce a case study of implementing this technology for a particular writing system, and use this to introduce the concept of text modes as a possible model for implementing governmental standards, publishing norms, or individual preferences at the document, application, or system level. The technology I want to talk about is formatting control characters. I don't think this is a formal Unicode term for the various kinds of characters in question, but it neatly captures their purpose. These are characters, usually invisible and ignorable in text functions such as searching and sorting, which can be inserted into text strings to affect how the text is presented, or potentially presented, to the reader, by requesting particular forms of glyphs, particular directional formatting, or special formatting for discrete text elements in specific writing systems. There are many kinds of formatting control characters, only a few of which are identified here. Some of them are specific to individual writing systems, others have more general purposes. In this presentation, I'm going to be talking about the first two, zero-width joiner and non-joiner, in the context of cluster shaping of index scripts. But the text mode concept with which I will end the presentation could easily integrate variation selectors. Zero-width joiner and zero-width non-joiner, pronounced by some people as zwidge and zwinge, have been included in Unicode since version 1. Ken Whistler identifies Joe Becker's implementation of Arabic and Devanagari scripts at Xerox as the proximate source for these characters. That work would have identified the usefulness of being able to force or prevent certain joining behavior in Arabic, as illustrated on the left in the Unicode core spec, and in index scripts to control different ways of representing conjuncts, that is, sequences of consonants with suppressed inherent vowels. The latter includes both generalized mechanisms of conjunct formatting derived from the Devanagari model, shown top right, as well as script-specific models for some writing systems, such as Malayalam. In both cases, the models tend to presume that the default presentation of a particular conjunct will be determined by the font, and the formatting control characters will be applied to affect exceptions to those default, although the mechanisms tend to favor traditional ligature forms of conjuncts as a default for many scripts, as in this Devanagari example. Within the prevalent OpenType layout model, there are 2 basic ways in which the zero-width joiner and non-joiner are implemented in shaping engines and fonts. Script-specific engines contain knowledge of Unicode-specified behavior for these formatting control characters in each script, meaning that their presence in text can be used to trigger or suppress individual layout feature lookups in the font. In the lookup code snippet shown on the left, note that the Devanagari half-form substitutions involve only the full-form letter and the halant, the Devanagari virama or vowel suppressor. When the Devanagari-specific shaping engine encounters such a sequence, in which the halant character is followed by the zero-width joiner, it knows to apply the half-form layout feature to the sequence. Similarly, if the sequence is followed by zero-width non-joiner, the shaping engine knows to suppress the default or half-form shaping and display the explicit halant form. In a generic shaping engine, as typified by the universal shaping engine invented by Andrew Glass, the engine contains no specific knowledge about the role of formatting control characters. This means that the zero-width joiner and non-joiner must participate explicitly in glyph processing lookups, as shown in this Sinhala example on the right. I will be talking at considerably more length about Sinhala shaping later. For now, note only the presence of the zero-width joiner, highlighted in orange, in the substitution code. Things sometimes go wrong. Script-specific shaping engines need to get their script-specific knowledge right, and need to be consistent and compatible for font makers and users to achieve predictable outcomes. I have recently been implementing Malayalam layout in a font, and testing my font and others in various environments. For reasons I'll explain with the next slide, Malayalam uses the zero-width joiner and non-joiner in peculiar ways and doesn't follow the general model derived from Devanagari. The behaviours do not map neatly to OpenType layout features, so Malayalam shaping engines are a kind of hybrid, notionally script-specific, but technically closer to the generic model of the universal shaping engine. Unfortunately, existing shaping engines provide inconsistent levels of support for formatting control character sequences in Malayalam. Only HalfBuzz successfully implements all the expected behaviours when implemented in font lookups. In the test on the left, Microsoft's DirectWrite and Apple's Core Text engines are correctly applying the pre-base forms feature to substitute the prescript ra glyph, but are then failing to reorder it before the base letter. As well as testing shaping engines, I tested a large number of Malayalam fonts with a variety of default behaviours and found that almost all of them broke when formatting control characters are present in text. Without examining the feature lookups in their sources, it isn't always possible to understand how the fonts are breaking. But my conclusion is that, given the failures of significant shaping engines and the majority of fonts, zero-width joiner and non-joiner are currently unusable in Malayalam text outside of very specific controlled situations. When things are working, however, shaper and font interaction not only provides shaping as defined by Unicode, but may also support some useful hacks. The standard behaviours for formatting control characters in Malayalam address two orthographic forms of the script: a traditional orthography, characterized by many ligatures and stacked form conjuncts, and a reformed orthography from the early 1970s that simplified many aspects of the writing system, dispensed with a lot of ligatures, and greatly reduced the number of stacked conjuncts. Broadly speaking, use of zero-width joiner and non-joiner in Malayalam is meant to enable traditional overrides in fonts with reformed defaults, and reformed overrides in fonts with traditional defaults. As illustrated in the core spec, the joiner character tends to shape traditional forms and the non-joiner reformed sequences. The first trouble with this is that the traditional and reformed orthographies do not constitute a simple binary. Neither orthography consists of a uniform set of forms common to all texts and all fonts, and the situation is further complicated by a reform of the reform promulgated in 2022 that reintroduced some traditional ligatures. The second trouble is that not all the distinctions between the orthographic norms are currently addressable via the mechanisms defined by Unicode. The two table rows that I have highlighted in yellow show vertically stacked conjuncts formed using zero-width joiner preceding the Virama sign. This is the same mechanism that is used to form conjunct ligatures, as shown in the blue rows. Unfortunately, this means that for Malayalam, unlike most index scripts in Unicode, there is no approved mechanism to produce all the various forms of conjuncts attested in text. On the top right, I show three different ways of writing the same conjunct, all of which are attested in Malayalam publications. The horizontal ligature form, shown in green, can be applied using standard Unicode behavior for zero-width joiner. The two alternate arrangements of stacked elements, in orange, are here formed using a hack that treats subscript forms as more like the separated forms that Unicode shapes using zero-width non-joiner. This enables finer control over the formatting of conjuncts in Malayalam. On the lower right, I have illustrated an additional hack to implement the distinction between traditional and reformed vowel signs, currently not possible in Unicode. This will complete the set of orthographic overrides and enable a single font to support different Malayalam text modes defined entirely using formatting control characters. A hack is a standard waiting to be proposed, so having figured out what works and what could work, I plan to write up a proposal to tweak and extend Unicode's specification of formatting control characters in Malayalam. Now I want to talk about Sinhala, because I believe its unique encoding model provides a useful case study for how powerful and necessary formatting control character support can be. Also, I happen to think it is one of the world's most graphically beautiful scripts. It is the primary script of the Sinhala language of Sri Lanka, spoken by about 18 million people worldwide, as well as being used to write Sanskrit and Pali. This engraved page from the early 19th century is not only lovely to look at, but especially interesting to me because it represents a transitional moment between the local palm leaf manuscript tradition and typographic forms influenced by European writing tools and print technologies. This is the first public showing of the new Sinhala typeface, which Fiona Ross and I completed this summer. It is founded on proportions established in 19th century metal types and inspired by those transitional manuscript dynamics. The encoding model for Sinhala in Unicode is distinct from that of other Indic scripts, which allow font makers discretion about default forms and exceptions. The Sinhala encoding explicitly requires as default the simplified modern orthographic style, in which conjuncts are indicated with a visible Virama sign, Hal-Karima. This means that the use of zero-width joiner character is necessary for shaping the other conjunct forms occurring in traditional Sinhala orthography and in Sanskrit and Pali texts. Zero-width joiner after the Virama sign produces either a reduced form for conjunct initial R, Rapaya, secondary Ya, Yansaya, and secondary Ra, Rakaransaya, or traditional ligature forms for some consonant combinations. Zero-width joiner before the Virama produces a special behaviours Sinhala script, conjunct forms indicated by touching together consonant letters. This feature of Sinhala script is very useful and powerful because it provides a way to graphically represent arbitrary conjuncts, which may occur in Sanskrit texts as a result of rules governing writing of Sandhi, that is, sound changes at morpheme or word boundaries, including vowel elision that can produce rare or even unique conjuncts attested in a single text. In scripts such as Devanagari, such conjuncts require many specialized ligature forms. In Sinhala, any conjunct not represented by a ligature or reduced form can be represented using touching letters. I love the systematic nature of this elegant and powerful mechanism. Note, by the way, the orange-colored R initial cluster on the third line. Zero-width joiner is present in this string, but the Sinhala font contextually prevents formation of the Rapaya reduced mark because the cluster also includes an above vowel sign. There is no standard clean way to write a combination of Rapaya and above vowel sign on the same base, and many fonts break when trying to display this character sequence, as shown in red. Here is a detailed examination of what is happening in the encoding of one of these Sanskrit clusters in Sinhala. This single cluster is using all three conjunct mechanisms of the script: a ligature, followed by a touching letter, followed by a reduced form Yansaya, all shaped by standard use of zero-width joiner. The cluster terminates in a nasalization sign. Sinhala touching letter behavior, as defined in Unicode, is one of those aspects of text layout that is easy to describe but challenging to implement. I spent a lot of time trying to figure out a flexible and efficient way to make it work at the font level, and I'm indebted to my colleague Patamid Godawata for giving me an idea that led to this current implementation. The Sinhala font contains 15 zero-width invisible join glyphs that are contextually inserted into glyph runs, replacing the zero-width joiner plus Virama sequence. Which of these join glyphs is inserted is determined by the right side shape of the preceding letter. This allows me to kern the first and second letters to the invisible join glyph between them, based on their shapes, such that they touch in a legible, visually pleasing way. So, we have seen how formatting control characters like zero-width joiner and non-joiner are powerful and, if correctly implemented in shaping engines and fonts, provide ways to control the visual display of text. But the technology is underutilized and hampered by usability barriers. In my experience across a wide range of scripts, I have observed that most users don't know how to deploy formatting control characters, or even that such characters exist and have specific functions within their writing system. When informed that the layout behavior they desire in their document is possible, for example, by inserting zero-width joiner after a Virama, they are likely to be further frustrated. How are they to edit existing texts? How are they to insert the formatting control characters in the precise location required within a conjunct sequence? Indic input and editing paradigms typically prevent caret insertion within a cluster, forcing deletion and retyping of characters from the end of a cluster if one wants to insert anything mid-cluster. Even if users are willing to do this, or more simply want to affect formatting while typing new text, they may find it difficult to locate the appropriate formatting control character on the keyboard. Here are the Windows and Mac OS keyboard layouts for Sinhala, as shown in the respective system on-screen keyboards. Can you identify how to input the zero-width joiner character? On Windows, it is hidden on this blank key, while Mac OS provides separate key states for combinations of zero-width joiner after and before virama. Neither system does a good job of identifying these mechanisms in on-screen keyboards, so users find them, if at all, through trial and error. Software makers could certainly do a better job visualizing formatting control characters in these kinds of input aids, but asking users to manually input formatting control characters is impractical, given how extensively these might be needed to affect particular orthographic styles across whole documents. And of course, users may be employing alternative input technologies, such as speech to text, implying accessibility issues around use of formatting control characters. These usability barriers are also an issue for someone in the admittedly rarefied situation of needing to perform systematic functionality tests on a new Sinhala font. I asked my colleague Khaled Hosni to write a text manipulation script that would use some options and rules to insert zero-width joiner into Sinhala text strings. Here are a couple of snippets from that Python tool. The first in which we define the scope of Sinhala in terms of Unicode characters, and the second showing the rules for identifying conjuncts that can take traditional ligature forms. The script is open source and available in the Tiro Tools GitHub repo. The tool enables text in Sinhala script, in this case Sanskrit, to be formatted in 4 different modes. The R, reset mode, removes formatting control characters to apply default simplified style. The Y option turns on reduced forms, Bara and Ya. L applies traditional ligature forms, the set of which is font specific. And finally, the C option turns on touching conjuncts. Here the output is color-coded, highlighting the clusters affected in each mode. For Sinhala, it made sense for the options to be additive. For another script, they might be exclusive. As well as enabling testing of my font, Khaled's script also provides a proof of concept for something I have been thinking about for a while. Text modes, defined via rule sets for insertion of formatting control characters, applicable to text at the document level. With appropriate shaping engine and font support, these text mode rule sets could activate, for example, distinctions between traditional and reformed Malayalam, or between the 1971 and 2022 reformed orthographies, and could do so independent of font defaults. Here's another example of a potential use. In recent years, the Bureau of Indian Standards has promoted Hindi-specific conjunct shaping in Devanagari, favouring horizontal layout with explicit halant over traditional vertical ligature forms. The traditional forms remain recommended for Marathi and Nepali, presumably also for other Indian languages using the script, and of course for Sanskrit. This is not uncontroversial. I have worked with some clients who have requested this BIS Hindi shaping as default Devanagari font behaviour, but also with publishers who have no intention of implementing it, concerned that it not only introduces an artificial distinction between the writing systems of Hindi and other languages, but also between modern Hindi and its own past. My anarchic view is that unless typesetting government documents, it should be up to publishers and other users to determine how to present in text the things they have to say. One way to do this is to recognize a BIS Hindi standard as a particular text mode, and to enable it to be applied to texts by rule-based insertion of formatting control characters. The behaviours specified by BIS for Hindi typography are all directly applicable using zero-width non-joiner, and the situations in which this character should be inserted are well defined. This enables the same Hindi text to be presented in different modes. Where in software should the text mode concept live? Where and how might rule sets for insertion of formatting control characters be implemented? I can imagine them being useful at various places where they might be applied anywhere from individual documents to system preferences. I encourage people working at various places in the tech stack to consider this idea and welcome feedback and suggestions. One possibility that occurs to me is that standardized modes, such as BIS Hindi or the different orthographies in Malayalam, could be defined in Unicode's Common Locale Data Repository, with rule sets expressed in some format defined by Unicode. An obvious place to implement text modes is in publishing workflows, where rule sets can be used to format text to conform to editorial standards or house styles. This would extend the typeface options available for many scripts, because publishers would not feel limited to individual fonts with appropriate defaults. The more interesting possibility, to my mind, is application of text modes in a buffered state between encoding and display, not affecting the underlying character strings but only how they are presented. This would enable the mode of text to be determined at the consumption stage, where text is read rather than where it is published. I imagine this being applicable to ebooks, news sites, social media, and other dynamic content. With robust support for text modes in software and fonts, we will be able to ask readers, how do you want your text today? Thank you.